cloud. Hi, everybody. Welcome to another exciting computer architecture class. I hope you had a good chance to look at homework 4 because homework 4 is due tonight at midnight. Be there or be square. It's on performance. I don't know if you can see that here. I'll hold it up to the camera. See? Performance. And so what I thought I would do is ask if anybody had any questions about homework 4. We know, I'll just review it for you real quick. There was Amdahl's law. There was speed up questions. There was some basic architecture, some virtual memory discussion. Let's see. We had a little thing about interrupts and interrupt control. There was something about general purpose microprocessor systems and architectures and with block diagrams. Microcontroller architecture. Flash memory was discussed. Double EEPROM was discussed. Let's see now. And that's it. NOR memory, NAND memory. And if you guys are up to speed on that, I'd like to cover homework 5, which should be available to you now. And homework 5 is on vector architecture. And a vector is really nothing more than a list of numbers. And vector architectures work on homogeneous lists of numbers. And homogeneous lists of numbers are rather important as an application. So homogeneous list of numbers, integer ED of 512, that's 512 integers in a row, that's a list of numbers. Float F of 1024, 4, I'm going to write 4, keep saying it, but it's not coming out. 1024, that's a list of numbers. Okay? So that's a basic idea, and if you think about it, these things are important to us because if you have a list of numbers and you want to do an operation on them, in MATLAB, you could say things like A equals A times B, where A and B are one-dimensional vectors. And when you're doing things like that, what you're doing is you're saying, I want to do the same operation on all the data. Single operation, multiple data. Let's think about Flynn taxonomy. Single instruction, multiple data. That's Cindy, isn't it? Now let's assume for the moment that you would like to do something else at the same time. Let's say A times B plus C, all at once. So now I have multiple instructions and multiple data. Multiple instructions, multiple data. It's a very interesting idea. So this is kind of a little bit different than what we've been thinking about in terms of instruction level parallelism. The vector architecture that allows us to do something to an entire stream of numbers like this is important because sometimes we like to be able to do what's called multimedia extensions or MMX type instructions. And multimedia instructions become very important to us when we're dealing with vector architectures that deal with data that is open-ended. I'm going to refer you in this homework to a paper which I wrote, and it's surprising to me how long ago it was, 2005. Wow, so 15 years ago, I wrote a paper. And what it did was it gave you an outline of a vector architecture called AltiVec. And AltiVec was Motorola's attempt to do multimedia streaming on their PowerPC. PowerPC is still alive today. And what they were able to do is come up with a CPU architecture, which is a little bit different than what we're able to see in normal CPUs. We would have a thing called the dispatcher, which is really little more than a finite state machine. And then it would take data and put it into an instruction unit for general purpose register computation, or it would take the opcode, the operational code, and put it into a floating point unit for a floating point register to operate on. Or, and here's the interesting thing, it had a special assembly language opcode called a vector processing unit, and then it had a vector register file. And what that would do is take an array of numbers and do an operation on the array of numbers. So one operation on an array of numbers, that is a single instruction with multiple data, and we call that SIMD. And that's the key for our streaming computations. Now, Amdahl says that we can find a fundamental limit to the rate at which we can increase the speed of the execution of our instruction. In the limit, as the speed up goes to infinity, our speed up is going to be equal to 1 over 1 minus the fraction of parallelism. But here's the interesting thing. The fraction in which you can parallelize is quite high if your goal is to do streaming processing. So for example, if you want to build a special purpose architecture for something like Amazon Fire Stick or Roku or whatever Google is offering for streaming, the Google Streaming Stick, I forget what they call it. You guys probably know because I don't have one. You might be very interested in making this vector processing unit quite large because your goal is to take an array of data and operate on it to do one sort of thing. And that might be to look up in a code book the data that's coming in and try and create large amounts of data on output. So the question then is, how big can this vector be? Back in the days when this was new, this was a 128-bit wide bus. This is sort of a big, thick bus. But if you're going to build chips that are meant to do signal processing for some application like streaming, you make it as large as you like, as large as is needed. And then all of this feeds into memory with various bandwidth. So this might be 128 bits, this could be 64 bits, that could be 32 bits. And all of it ends up going into a place where we call high performance memory inside of the CPU, the cache memory. That cache memory is not the memory you buy in the store that you plug into a DIMM slot. That's the memory that comes inside the CPU or is put in a special slot right next to the CPU. And this can come in various flavors, L1, L2, L3, and the size is inversely related to the performance. As you get into larger cache sizes, they get slower and somewhat less expensive. And then the whole instruction stream comes back with outputs that go into the dispatcher. So the cache might prefetch instructions so that the dispatcher can decode the next instruction and then decide where the data should go. So this is capable of dealing with instruction sets that we now know today by various marketing terms. AltaDec is one. MMX was relatively new in the day. Then came the streaming SIMD extensions, SIMD being a Flynn taxonomy reference known to the CPU designers. And then they came out with SSE2 extensions, and people who made use of the assembler for these instructions basically made their code incompatible with the older processors. That is, if you had a game or something like, you know, a flash decoder that made use of these instructions, well, we couldn't get good performance if from your CPU if your CPU didn't implement the hardware for those instructions. So we needed that. We needed it. And then if you read the paper that I wrote, you'll see how you can write your code to take advantage of this. And what I'm going to do is I'm going to show you how you can essentially vectorize. This is, I guess it's not decent English. I don't know what to tell you. Vectorize. What does it mean to vectorize? What it means is to indicate to the compiler that you want to use these instructions without having to write the assembler yourself. This is so important because when you try to write code, if you write the code in an inefficient manner, your compiler will not know to use the vector processing unit. But if you write the compiler directives in such a manner so that the compiler, any compiler, worth its salt, can recognize the vector processing, then the compiler will effectively do the work for you, at least some of the work. So let's see what happens if I want to add n numbers in an array and return the results. So normally what I would do is I would say something like this. Sigma I equals 0 for I equals n, a sub I is equal to a sum, right? That's how I say it in math. And that's very clear. Everybody understands this, makes perfect sense. How do I implement it? And the answer is, well, I start with a return value. That's going to be a 32-bit float. And I'm going to take, you know, some sort of a name, let's call it sum or sigma. And then what we're going to do is we're going to pass in our vector. Vector is a fancy name for an array of homogeneous quantities. They're all the same, they're all floats, they're all of primitive data type, but they're passed in as a reference. And the number of elements that I want is n. And I'm doing this not in Java, but in C, because C is going to have to pass in the total number of elements that you want to sum. And what I normally do for I'll call this SysD, right? So this is my SysD, single instruction, single data code. This is the inefficient, wrong way to do it. I'm going to show you the wrong way. It's perfectly obvious. It's the way you're going to do it when you take CS131. They don't teach you how to do this in CS131 because it's an advanced programming topic. So then if you go in and you say, well, how do I add all these numbers? They say, well, I make up an integer I equals 0. I declare my summation. That's an auxiliary variable. S equals 0. Then I write my little for loop for I equals 0 while I is less than n, I plus plus. This is normal idiomatic code, which I know immediately what you're going to say. Oh, it's just S equals S plus A of I. This is boneheaded code. I know how to write this from CS131 class. And after I'm done, I return the summation S, and I'm done. And this is perfectly valid code. This works on a SysD machine. Let's compare it to SIMD code. SIMD code is different, right? SIMD code basically says, let's do this n elements at a time, where n is the number of stages in our vector processing unit. In other words, we have to unwind the loop. So now we're going to do the same exact thing, write the same code. It's going to give us the same exact result, but it's going to work differently. It'll make different assembler, and it's going to run way, way faster. We're going to take advantage of a 4-stage pipeline for vector processing. And so what we'll do is we'll call this And we want to keep the basic structure, but we're going to give it a different name because we want these two different programs to be co-resident so that we can benchmark them, right? In other words, after I'm done writing this code, and then I'm going to write my new code, I want to see which one is faster, so I have to be able to know how to benchmark. That's so important. So I'm going to call this one sum V for vector. V is for vector. And so now I put in my same exact arguments, right? Same exact arguments. And what I'll do is I'll do the same exact initialization, integer I equals 0. And then what I'm going to do is I'm going to use a directive. A directive is a special thing that you use to signal to the compiler your intentions. And so what we're doing here is we're creating an auxiliary store in the cache of the CPU using the directive register, which is part of C and C++, but not Java. And we'll say we're going to register these 4 floating point numbers, and we're going to set them to 0. And now I'm going to use these 4 floating point numbers as a homogeneous vector. I'm going to stuff the 4 floating point numbers with the A vector input coming in. This is A. And then what we're going to do is we're going to do that 4 elements at a time. So we say 4 I equals 0, while I is less than n. And then what we'll do is we'll say I equals I plus 4. And now we do what's called unrolling the for loop. So S of 0 is equal to S of 0 plus A of I. S of 1 is equal to S of 1 plus A of I plus 1. And you can see how this is unfolding. S of 2 is equal to S2 plus A of I plus 2. Right? And that goes on and on. You can unroll this for loop however you like. In fact, if you think about it, it's looking an awful lot like VHDL. S of 3 is equal to S of 3 plus A of I plus 3. So now we've gone through the 4th stage, and now we can compact this vector by returning S of 0 plus S of 1 plus S of 2 plus S of 3. That basically takes 4 elements at a time. And it's kind of an interesting idea. It gives you a different assembler, unrolls the for loop somewhat, and by unwinding the for loop, I get a speed up, believe it or not, of 2 microseconds. And that was, well, perhaps back in 2005 when I was benchmarking this. And you can envision how you could do this with 8 stages of pipeline. If you read the code, you'll then see how you can get to AltiVec-friendly code. And that AltiVec-friendly code is essentially going to give you a much faster mechanism for getting a speed up. And so that's a question, how much faster is it? I was getting 4.5 times speed ups. And it was remarkable. And I looked at this and I said, geez, we've got to change the way we write our code if we want to go for speed, right? Why doesn't the compiler do this for us? And well, the compiler it's not that smart and all these other things. And what do people do when they're making hardware? And that hardware is effectively trying to create a high-performance machine and you don't have a library that automatically detects the presence of your vector processing unit and optimizes your code for you, right? I mean, you're wasting the hardware. So you need that mechanism in here to kind of signal to the compiler, registering these things, puts it in cache, breaking the for loop up into 4 different chunks and having it add together 4 at a time. These are the kinds of things that will really accelerate your code for things like AltiVec, SSE2, SSE, and MMX. And so is it materially changing the code? No. What it's doing is it's refactoring the code. It's changing not what the input and output is, it's changing how it's written. And so that refactoring requires that you do extensive testing. Because if you're going to start unwinding stuff like this 4 at a time, what's going to happen if you're not running with data that's an integral power of 2 or an integral power of 4? Will this die? Will it run off the end of the array? You really need to test this stuff before you deploy it into a pipeline processor. So refactoring is a form of extreme programming. It's a methodology that requires testing. There's an old joke about methodologists. What's the difference between a methodologist and a terrorist? Do you know the answer to this one? No? The answer is you can negotiate with a terrorist. So this is a software engineering thing. So there you have it. The basic idea on vector architectures and how you would see a means of creating an improved throughput. Now, when you have these specialty throughputs, specialty architectures, you wonder why would I have that? What on earth could possibly justify this? I went to the graphics card store. NVIDIA wants to sell me Titan 5 graphics card. Titan 5, oh goody, that sounds good, I want that. They want to charge me $3,000 for a graphics card. And I think, oh, that makes me hopelessly middle class. What do I get for $3,000? And the answer is 21 billion transistors. I'm like, holy mackerel, that's a whole bunch of transistors. And what do they do with all them transistors? And the answer is they do deep learning at 110 teraflops. And I looked at that and I said, holy mackerel, that's a lot of teraflops. And how do they pack 21 billion transistors in? And the answer is they go to Taiwan Semiconductor and they make 12 nanometer wide transistors using a thing called FinFETs. FinFETs are little field effect transistors with fins on them. They're 3-dimensional. And so they say what they have, and this is kind of interesting, and it's the answer to question 16, so I'm sort of skipping ahead, but I just thought this hardware was remarkable because of how middle class it made me feel. Because do I really need to spend $3,000 on just the graphics card? And if I got such a card, what would I put it in? Because I probably need a power supply that draws enough power to run a hairdryer. And it's going to throw up the heat of a hairdryer. And it's going to be sitting there depreciating rapidly because these cards will go obsolete and be discontinued in no time. And besides, what is the market for deep learning? Are there like, I thought the market was for gamers. That's the market. Nobody cares about scientific visualization and deep learning, but these guys are doing it, right? I mean, they're selling, you know, and you say, well, what am I building all this hardware for? Apparently because you can just make up a price and sell it. And you know, I don't begrudge them the $3,000 because nobody else is doing this. However, if you really wanted to have access to this card, you could kind of rent it on Amazon Web Services, and they'll let you do the same thing on a per hour basis without having to spend $3,000 on a card. I'm not quite sure how much it is, but it's not $3,000. I'll tell you that right now. So what does it have in it? Well, we heard before about the CUDA cores, and they're kind of little SIMD machines themselves. But then it says here it has, and I never heard of this, tensor cores. Tensor cores. And I think, oh, that's just more marketing. What could that possibly do? Tensor cores, this is real specialized stuff. So tensor cores multiply two 4x4 floating point 16-bit matrices. So this is single precision floating point for sure. And so A times B is what they do. And they add another number plus C, another floating point 4x4. And then they return a value B. This is what they do. And there's 612 of them. And between all of those things plus the CUDA cores, you get, this is remarkable, 110 teraflops. Teraflops. I don't think they should call them teraflops because they're not terrible. They should call them horror flops. Maybe they're horrible. So it's a fused multiply add. That's two instructions. This is not SIMD anymore. SIMD is single instructions, multiple data. I got two instructions. So now I have multiple instructions, multiple data, right? Because these are vectors. Well, they're actually arrays. And they're being used because deep learning apparently needs these things. And maybe other things, other people need them too. I don't know. There's 612 of these guys running in parallel. So I'm now thinking this is more like a MIMD architecture. And that's the answer to question 16, which is about the NVIDIA Titan 5. You know, they've come up with a piece of hardware that sounds incredibly expensive. And I said to myself, not expensive enough. Because this is what I do. I go to the Bentley dealer in Greenwich, and I kick the tires, and I go, not expensive enough. So then I said, what else you got? And apparently they have this other thing, just because I didn't feel hopelessly middle class enough. And in this other thing, it's a Quadro RTX 8000. Okay, that's definitely a marketing name, all right? So we went from the Titan 5 to the Quadro QUADRO, what do we call it? RTX 8000. Okay. 8,000. No kidding. There's people in marketing, they probably went to Harvard, and they sit around and they brainstorm about this stuff, and they come up with new names. So this is the name they came up with. It's all marketing. And then they came up with a price. I guess that's marketing too, because it's whatever the market will bear. And if you want one of these things, you can get it for the low cost of only $5,500. So that's a little bit more expensive than the other one. And you're probably not going to pop it into your Walmart desktop computer, although I do these sorts of things myself. And so then it says, what do I get with this? Oh my gosh, this is so expensive. How do I possibly justify a Quadro RTX 8000? You know, just imagine the look on your parents' face when you say, gee, Mom, and Dad, I really need a Quadro RTX 8000 for $5,500 because I have to run MATLAB at school. I need it for my freshman classes. Or I need it because, the real reason, so that I can play Doom. That's the real reason. And what does it come with? And the answer is 48 gigabytes of, I had to look this up, GDDR6. What the heck is that? And why do I need it? My grandma is famous for her sayings in my family. And one of her famous sayings is, what do you need it for? $5,500 graphics card? What do you need it for? And what did you do before you had that? And I'm looking at this and I'm going, 48 gigabytes of GDDR6. What the heck is that? Is anybody out there in Zoom land know? You guys are quiet. How many other people here? I'm just going to poke my finger on the camera here. Sorry for my thumb. Oh, yeah, there's a lot of people out there. I'll bet you there's somebody out there who knows the answer to this. What is the GDDR6? You might have to use the Google. So it's RAM. This is RAM. Random access memory. And it's dynamic RAM. Oh, here it comes. 6th generation video RAM. Yeah, maybe so. Maybe 6th generation is correct. But it is DDR. This is double data rate. And later, I'm going to go back over these terms, and we're going to talk a little bit about what they mean. And then it's also dynamic RAM. And it's synchronous. So there's a clock involved. And yes, I would guess it's probably regarded as 6th generation. So that's a mouthful, GDDR6. Let's think about this now. I think I know what RAM is. I kind of know what dynamic means. What is dynamic RAM? What is that? Did we talk about this? Dynamic RAM? So dynamic RAM, I guess there's two kinds of RAM. There's static, and then there's dynamic. And I'll just call it RAM. Two kinds of RAM. So what's dynamic RAM? Dynamic RAM is the cheapest possible RAM you can create. It consists of a capacitor. And what you do is you write a 1 or a 0 to the capacitor, and it holds a charge which holds the 1 or 0. And because capacitors leak and lose their charge, you have to go back and refresh the capacitor occasionally. That's dynamic RAM. They call it dynamic because it's based on the capacitor. Static RAM, that's a D flip-flop. That's static RAM. Both are volatile RAM examples, right? Because if you lose power, the D flip-flop doesn't retain its state. Moreover, if you lose power on the capacitor, it does not retain its state. So these are both volatile RAM types. There are non-volatile RAMs available, but these aren't that. And so that is dynamic RAM. And now what's this double data rate thing going on here? What's that about? Well, when you go to write to RAM, it takes some time before the data is guaranteed to be valid. When you want to retrieve the data, it takes some time before the data is guaranteed to be valid. So what you do is you dual band the RAM. You alternate between asking for the even addresses and the odd addresses when you're writing or reading. And so then if you want to write to address 0, you can skip ahead while it's writing to there and write to address 1. So effectively, that dual bands the RAM. In fact, if you really want to make high performance RAM, you quad band it. So you write to bank 0, 1, 2, and 3, and then go back to 0. And while you're doing that, it's writing out to the different banks. And so these double data rate RAMs are writing on the up edge of a clock and then on the down edge of a clock. And this enables you to effectively strobe data out at double the rate. And as RAMs have been getting faster in general and more dense, these things have been going faster and faster. And we know what synchronous means. It's clock. And in fact, if you think about it, the static RAM is generally clocked as well, because D flip-flops need a clock. If they're synchronous flip-flops, in general they are. So this is an interesting idea. And if you go in and, I don't know if you're going to buy one of these cards, you know, oh, 48 gigs, I don't think that's enough. And it's not expensive enough because I want to spend more money. So there it is. If you look at question 17, the answer is it's RAM, it's double data rate RAM, and it's synchronous double data rate RAM, so it's all of the above. And you're getting, I don't know how many transistors in the, you guys can Google this one, the Quadro RTX 8000. I'll bet you it's, I'll bet you it's 40 billion transistors, but I'm not sure. I'd have to Google that one. It's a product, okay? And by the way, in 10 years, I'll be able to get one cheap on eBay. Although I probably won't want it by then. I'll want the next big thing, which will still cost $5,000. Okay, so there you have it. Latest and greatest stuff. So now we've got the question about SIMD. Where did this basic SIMD idea come from? Vector architecture, single instruction, multiple data. Who thought of this idea? Anybody know? It's an invention, right? I mean, well, let's say the cavemen didn't have one. I don't think. Probably one could make a compelling argument that in the case of SIMD, the real progenitor was Alan Turing. And Alan Turing's paper from 1946 and you may remember his name from such terms as Turing equivalent, although very few people would know that he came up with the idea of SIMD. Turing was pivotally involved at Bletchley Park, where he was helping to design decrypting automatons. One was called the bomb, which was responsible for decrypting Enigma, and another one was called Colossus, which was also responsible for decrypting the more advanced Enigma machines. And Colossus had 1/10 of the number of tubes that ENIAC had, and was not a general purpose electronic computer. It was special purpose, but still a very interesting machine and quite ahead of its time in terms of when it was created and what it was doing. Let's see now. So that's the answer to question 8. The original SIMD idea came from Alan Turing. Now we have another question here. Is a vector processing unit a SIMD machine? And the answer is yes. Yes, it is. So vector architectures generally are SIMD. And in fact, there is a thing called the digital signal processing chip. A DSP chip is really nothing more than a vector machine. And vector machines are meant to do streaming processing. That is processing of data that is homogeneous and arranged in a row. It's array processing. Let's think about the multiple instruction idea in context. Let's try and create what I would call a Flynn taxonomy outline so that we can see where we are with respect to the different types of architectures. And we'll start off by classifying things by instruction stream. You can have one, or you can have many. And then what we'll do is we'll further classify things by the data streams. And here we'll have one, or we'll have many. So if you have one instruction at a time and one piece of data at a time, we call that SISD, or single instruction, single data. If you have many instructions, but a single data point at a time, you call that MISD. Okay, so then I understand SISD, right? That's what we're normally used to. So we'll call that traditional von Neumann CPU computing. But now comes MISD. This is pipeline. So therein lies the place where you might find multiple instructions, single data point at a time. You're using superscaling. You build a pipeline like an assembly line. Now comes one instruction, many pieces of data. That's your SIMD right there. And so now we have the vector processing units and fine-grained data parallel machines, but really VPUs is where we're at. And in fact, DSP chips can be doing this sort of thing. And then comes, I'm going to read this again because I keep forgetting. The Quadro RTX 8000 or the NVIDIA Titan 5 with 110 teraflops and 610 tensor cores. And gosh darn it, how did they pack all those little tiny cores in that itty bitty can? So then here it is, it's MIMD, multiple instructions, multiple data, and this is a true multi-processing machine. Right, there's multiple processors and a whole bunch of SIMD stuff stuffed into there. And here's the question, all right? The question is, consider the Flynn taxonomy. A DSP chip must be MISD. True or false? This is question 11. Well, we can see right here, DSP chips are not MISD, they're SIMD. So this is where I would, sort of just look it up and say, yeah, DSP chips are SIMD. That's certainly false. What do you think of that? That sort of outlines everything. So processor organizations. This is what I would call, I'm going to put this in a different color because I keep writing on the same area. Let's see, how about red? So we'll call this uniprocessor. I think that's uniprocessor. Then comes SIMD, that's the vector processor, but sometimes people say it's an array processor. And if it's an array processor that hangs off the side physically from your normal architecture, they call it a systolic array processor. Then comes multiple instruction, single data, and that's your superscaler. And then comes multiple instruction, multiple data. And this is where you might have the so-called symmetric. Multiprocessor. And so your Titan 5 is an example of a symmetric multiprocessor system. And that's kind of an interesting thing. That's what you're getting for your $3,000 or $5,000. And by the way, they make more expensive boards too. Do you have to buy one of these things to use one? And the answer is no. Amazon Web Services will give you an introduction to these expensive deep learning systems by going onto the AWS website and getting a micro instance of an EC2 server, which they'll give you for free. And then you can try and see what you can do to finagle your educational status to start using some of these interesting deep learning technologies to do whatever. I'm still not convinced I know quite what to do with all those CPUs. I find it a little, well, a little intimidating, isn't it? I can barely program one CPU. I'm supposed to program 600 tensor processors. It makes me all tense. So that's a there's a new graphics card out they call a ray tracing machine. This will be a SIMD architecture, single instruction, multiple data. It's a pipeline. So here's your application, and it feeds into the model transform. And that goes into another transform called the view transform. And that goes into another transform. This is all 4x4 matrix multiplications, actually. And they do this this thing called homogeneous coordinate processing. And in homogeneous coordinate processing, the coordinates are X, Y, and Z, and they're being sheared and scaled, translated, and rotated about 3 axes all at once with a 4x4 matrix multiplication that's applied to all the points. And so what you have is a pipeline that effectively has to go through this process to determine what the value will be of individual pixels on a screen. So the lighting will do things like take a dot product with the normal onto a geometric surface, and then you'll do a perspective transformation. This all goes on inside the graphics card. And then you do whatever else you need to do to chug out basically an array of pixels that can be displayed on the screen. Pixels. And the application will start with geometry, and the output will be an image that gets rendered. And there'll be places where memory will feed textures, and they'll call this the graphics pipeline. So you'll have essentially a SIMD architecture, and that is question 13. That's looking more like a SIMD architecture. Lots and lots of data going through the same exact process, the pipeline. And that's essentially, I guess, what I would call the gist of homework 5. The rest of it is kind of like, I don't know, little bit more on the order of detail. Like, where would I find SIMD? And the answer is anywhere you find vector processing units. So I can find this here in Alphabet, which is a marketing term that came out of Motorola, right? MMX, another marketing term that came out of Intel. In fact, they used to have little stickers that they put on the laptops that had MMX next to the Intel inside. SSE and SSE2, I don't know if they ever had stickers for that stuff. You know, what happens is John and Jane Doe from Anytown, USA, do not appreciate the little sticker that says MMX, because they don't know from SIMD and MIMD and Flynn taxonomy, right? In fact, I make a claim, and I often make it, you may have heard me make it before. Intel has done a remarkably poor job in informing us about the architectural advantages of using Intel versus, let's say, AMD. And AMD has not done a great job either. I mean, why should I use Ryzen? Is Ryzen better than Raisin? I don't know. I mean, this is, what the heck is that about? If you're going to take time to try and sell $1,000 chips, you ought to be able to tell people why they need that. The consumer, as far as I can tell, doesn't care. It's dark in the box. All they want to know is whether or not it runs their application. And usually their application is something like Word and Excel and some Microsoft Office suite, and that's it. Although some people really care about playing Doom. I don't know how many people are sitting around doing deep learning at home. Do people do that? I don't do that. Does anybody here in the Zoom audience do anything with deep learning? Nobody. Not in our class. Okay, well, I'm just checking. These are not, applications. All right, I'll tell you this. The graphics pipeline is a mainstream killer application because it lets you play games. That's where the money is. It's not in scientific visualization. I don't think it's in deep learning. But you know what? If they can sell graphics hardware and make money at it, I could go, or deep learning hardware. Deep learning hardware. I mean, I can understand them selling graphics hardware, but deep learning hardware? Really? People want that? I would have said no way, but they do it. So what do I know? So here comes another question from homework number 5. Here is a MISD, multiple instruction, single data. And what we're going to do is we're going to go into the instruction pool. There's a bunch of different instructions. And what we'll do is we'll have different processing units. And we'll have data. And the data will be piped to both units at the same time. That might be useful if we're dealing with some sort of a redundancy, right? Let's assume I want 2 different processors to do the same computation. So if we're doing that, I can kind of see why I want to make sure that the computation's answer is correct. So I can make sure it's correct because I'll feed the same computation to both processors. And I can do pipelining this way. So the pipelining is good too, because I can do something over in here where the output from this processor goes into the input of that processor. That might be good. So that could be a nice pipeline that I create. Maybe that's part of my deep learning pipeline. I don't know. Or certainly my graphics pipeline. Let's find an example of MIMD outside of the ones we've been talking about so far. Suppose I have multiple processors simultaneously executing different instructions, as could be shown in here, and I want different data. So here's data set 1, data set 2. So now I can do some sort of MIMD thing, right? Data's coming from different places, multiple data streams. Suppose I had, where could I find this? A network of workstations. That's a good one. So I got workstation 1, workstation 2, ... workstation N. And this network of workstations goes to a file server, and the file server dispatches to the network of workstations different jobs, right? And workstation 1 renders frame 0, workstation 2 renders frame 1, all the way up to workstation N, which renders frame N-1, and presumably they all take like an hour to render. By the time we're done, maybe because there's so much overhead in the CPU, that we're so CPU bound, we don't have to worry too much about the images all hitting the network at the same time. Maybe they even render at different times. So that's question 6. You can have multiple autonomous processors, and you could come up with a multiple instruction, multiple data, or MIMD architecture. So this is MIMD. Multiple instructions, multiple data. Network of workstations. This works great, provided you're not overwhelming the file server with I/O. And that I/O is going to represent a sequential thing, unless you have multiple file servers and multiple networks with isolated traffic, which you can have, no doubt, no doubt, especially if you have some sort of an ether switch isolating one workstation and its file server from another. So, or each workstation could have its own file system. In fact, if you think about it, desktop computers almost always have their own file system. They have a hard drive. So if you tell the desktop computer to go do its rendering or its computation, whatever that may be, and then give you an answer later, it could be like hash this thing for Bitcoin, the amount of communication required is quite small. And yet the amount of computation required could be quite large. And so that's perfect for embarrassingly parallel programs. That's just what we want, an embarrassingly parallel program. And Bitcoin's a great example. In fact, if you think about it, I think cryptocurrency is a big market for NVIDIA, right? I get that the tensor thing does deep learning, but what you really want is a bunch of processors that do relatively little, like hashing Bitcoin solutions for Ethereum, and then you can essentially make an efficient Bitcoin miner. And if that's what you're trying to do, I get it, right? I mean, people really want that stuff. You're selling shovels to a bunch of gold miners. And making shovels is really where the money's at. So let's see now. Fermi. Here's more NVIDIA stuff. I like the NVIDIA stuff because it's a great example of cutting-edge computer architecture. So, I mean, these guys are doing stuff and selling stuff that you really don't see elsewhere. Like, what other company will sell you a graphics card with 512 cores? That's the Fermi card. And they call this a GPU, where GP is general purpose graphics processing unit, GPU. And the GeForce 8800 has 512 CUDA cores. So that's CUDA, not the other one, which is tensor cores. And so this enables you to do multiple instructions with multiple data because you've got a lot of cores. They can all be working on different instructions at the same time, and the data can be distributed to the different cores too. So that is a great NIMD example. Great NIMD example. But you can also do a single instruction multiple data because each one of the CUDA cores has a vector processing unit. So because you've got a lot of cores, each one of which has a vector processing unit, you can also do SIMD. So you can vectorize your code, as we saw in the past. It may require rewriting the code somewhat, unwinding for loops, for example. But you can also have multiple streams going through multiple cores, so you can have both SIMD and MIMD. So you can have both. It's not unreasonable to have both. That's a MIMD architecture overall with vector processing units on each one of the CUDA cores. And that is quite interesting because it leads you down a path of, let's say, I'll call it speed optimization hacks. Right? You could sit there and program the heck out of these things in order to try and maximize your throughput. When somebody promises you a peak throughput of 110 teraflops, the promise is you'll never go faster. You will almost certainly go slower unless you happen to work for NVIDIA and you're an expert at programming their hardware. I think there must be people who don't work for NVIDIA who are expert at programming their hardware, but I imagine the people at NVIDIA are better at it than everybody else in general. So that's Flynn taxonomy. I guess we've been beating a dead horse on it. I keep going back to the NVIDIA stuff. I know it's, I like to find examples from ATI that are anywhere near as good as what NVIDIA is doing. Nobody can touch it. I mean, no kidding. The loop unrolling is just the tip of the iceberg when it comes to doing optimization for vector processing. Here's another one, and this is sort of an important thing. And it's generally true for relatively simple computations. How am I doing on time? Good, all right, that's fine. There's a basic row major versus column major programming hack. Has anybody ever heard of this? Row major versus column major? This is question 15. Okay. When you do two-dimensional array processing, arrays, I'm just going to do this with a 3x3, can be organized this way. 1, 2, 3, 4, 5, 6, 7, 8, 9. Or, and they call this row major, or they can be organized in this way. 1, 2, 3, 4, 5, 6, 7, 8, 9. The numbers are actually addresses in memory. If you write a for loop, let's assume this is the direction which we call the row, and this is the direction which we call the column. If you write a for loop, you want the column to iterate, then you can increment the row, and then the column iterates, and you increment the row, and then the column iterates. That's iterating through the array in row major. If you have column major, you want to increment the column more frequently than you increment the row. This will enable you to have a principle of locality. That principle of locality will enable the RAM access register, the virtual memory processor, to prefetch all of the data and put it into cache ahead of the CPU so that you can effectively do this processing without causing what's called a cache miss. If you have a cache miss, your program could run as much as 6 times slower. If your cache miss is being generated, for example, in very long columns, and you're going column to column first because you're column oriented, and this is row major or something, you go this way, and you're skipping around in memory, and you're not able to prefetch. This is so important because if it's a ginormous multi-gigabyte image, all you're going to do is be thrashing as you go from one pixel to the next. And it will be completely unnecessary because you've accessed the array in an inefficient manner. So when you're doing two-dimensional image processing, a lot of times what you'll see is somebody simulating the two-dimensional array, and they'll say it's like x times h plus y, x times width plus y. And then if you do that, the x and y are basically just making a single number, which you can use to access a single dimensioned array, and you'll always know that you're going in order by incrementing y more frequently. And this multiplication could be extracted out of the argument, although many instructions are available now that will do a multiply and an add in one CPU cycle. Multiply add is available now in a single CPU. Any compiler worth its salt that knows this will see the multiply add and reduce it to a single cycle. But if you start to do something where you're accessing inefficiently, you're going to pay for it in time. So then the question is it always better to access 2D arrays in row major in order to avoid a cache miss in Java? And the answer is false. It's not, because it's not known if Java implementations are row major or column major. It's not a part of the Java language specification. You can test and figure out which one's faster, but unfortunately, it might change as you go from one machine to another, or even one compiler to another. So that is a problem. And that's why you see this for simulating two-dimensional arrays more frequently than you'll see something like a doubly nested for loop. In C, it's row major. In Fortran, it's column major. So it's not even consistent when you go from one language to the other. And so this is a critical problem, and this is the solution right in here. That's that word is an approach to a solution. So let's see now. You've got a little homework assignment there, and there's reading too. So you should be reading Java optimization for superscalar and vector architecture. I'm holding it up so you can see. I'll put it up to the camera. See that? And that is actually a link. There's a link to that in the homework 5 as part of the instructions. So when you start homework 5, you'll be able to see that link. And that is, I think, oh, here's another one. Where would be a common place where I could find single instruction, single data computing? Susie. Single instruction, single data, where could I find it? That's question 2. It's here. We use it all the time here at Fairfield. And the answer is Arduino. Arduino does that. Arduino. Old Pentium 4s will do it, but I don't think anybody has a Pentium 4 anymore. So that's the answer to question 2. They still exist. SysD machines, 8-bit toaster controllers, they're out there. Let's see what other questions didn't we do yet. If you have multiple instructions, single data, versus single instruction, multiple data, where would you expect to find data parallelism? And I think the Zoom folks ought to chime in now. You guys awake out there? Is there anybody left? I'm just checking. Oh, yeah, there's a bunch of people. So where would I find data parallelism? MISD or SIMD? I don't think you're paying any attention.
Would it be SIMD?
That's right. There's multiple data will give us data parallelism. MISD gives us instruction level parallelism. SIMD gives us data parallelism. And that is the answer to question 3. So that's good. So we're getting it. Let's see. I think we've gone through just about everything. I'm going to, based on the attendance of today's class, I think what we're going to do, and I'll send out an announcement to this via email, I'm going to combine the 2 sections because it seems like a lot of people are staying away. Maybe it's because of yellow alert or something like this. But if I can get critical mass in the classroom by the combining of the 2 sections, I will. You guys shouldn't feel obligated to come in. I get it. You know, stay away if you feel like you're, you know, vulnerable. But what we'll do is if you feel like coming in on both days, Monday and Thursday, I think we should permit it, just based on the attendance here today. I can't see any harm in it. We should be able to do distancing. So I'll send out an announcement to that effect. That's all the time that we have for today, unless there are some questions. Any questions out there? All right, well, have a good day and stay safe, and thank you for your attention.
Thank you.
Thank you.
Thank you.
Thank you.
Thank you.
Thank you. Thank you.
Thank you.
Stop the recording.